This is the lecture for Wednesday, October 31st. Happy Halloween. Last time we were talking about rotational motion and analogs between linear and motion and angular motion or rotational motion. Rotations. We said things like we have displacement, so we have maybe some delta x here, and then we have change in the angle. We had a linear velocity v here, we had an angular velocity omega. Okay. And we had linear acceleration a, and then we had an angular acceleration. One thing we added last time was, in the case of linear motion, there was the notion of mass, m. And mass m appears in all these formulas like Newton's laws. We're going to make the angular, or we already made the angular analog, what corresponds to mass, and we said it was the moment of inertia. Now we didn't really do anything. We didn't really do anything with the moment of inertia yet, but we will make this connection and do something with moment of inertia in this lecture. So let me add to this list of analogies between linear and angular. So there was force for the linear case, some force vector F, and the corresponding thing on this side is the torque, tau. All right. We won't be talking about torque quite as a vector yet. We'll be talking about clockwise and counterclockwise. So the notion of torque as a vector will be coming a bit later once we talk about cross products. Okay, so I've introduced the notion of torque. Let me define torque. So torque, as I said, it's the analog, the corresponding principle that corresponds to force, the analog of force for rotations. All right, if it's not clear what I'm talking about, if I have an object, let's say this water bottle, there's a net force, I push it, it accelerates, okay? But if I take this water bottle and I unscrew the cap, I have to exert a torque, a twisting, and that causes an angular acceleration if I twist. Okay. So that's what we're talking about here, is this twisting type of torque that rotates something about some rotation axis. So let's consider maybe having a little nut here, and we have a big, let me draw it sort of rather large, we have a wrench. It's a very simple wrench. Okay, and let's say I made the wrench a little bit bigger than I planned to. And this is the rotation axis. Rotation axis. So we have a little wrench here that's rotating this little nut, and I'm going to, let's say, push on this wrench with some force. Let's say there's some force here, F. And this is the rotation axis, so there's this axis coming out of the page around which things rotate. And that rotation axis, I'm going to draw a vector from the rotation axis to where the force acts. And this is what I'll call the R vector, the lever vector, the R vector. Here's a force, here's the R vector from the rotation axis, and let's say there's an angle phi between the two. Okay, so we have this wrench, we push on it with some force, there's this distance r between the rotational axis and where the force acts. Then so that's force. So then the magnitude of the torque is tau. That's the symbol for torque, the Greek symbol, small symbol tau, the small letter tau, is equal to the magnitude of the position vector from the rotation axis to where the force acts. So r is just the magnitude of r. As usual, f, just plain f, is the magnitude of the force f. Okay, I'm going to use that notation. Then the magnitude of the torque is r times f times the sine of the angle between these two vectors. Okay, so notice it's not the cosine, this is the sine. It's different from dot products. The torque has units of, let's try to figure it out. The r has, it's a position vector, so it has units of meters, and f has units of newtons, so it has units of newtons per meter. So it's the same in some sense as energy. However, torque is really quite different from energy. It's actually a vector. We'll talk more about how it is a vector in a moment. So let's not write this in joules, but just keep this as newtons times meters, just so that we don't get confused between torque and energy. Now let's talk about the direction of torque. So we can have different kinds of torque. So the torque about a fixed axis, as we've been doing, so there's some fixed axis around which you can rotate, can be clockwise, or let me do counterclockwise first. It can be counterclockwise. Sometimes people write this as CCW, or clockwise, which is a CW. So here's an example. Suppose we have this lever arm R. Here's the rotation axis, and there's a force like this. Then what we do is we think about, if I have, that's a little bit too short, but if I have a force pushing like this, think about how it's twisting. It's twisting in this direction. It's twisting in this direction. In this direction, okay? It's trying to make it rotate like this. And this is what we call counterclockwise. Counterclockwise. So the torque is counterclockwise. Your textbook likes to call counterclockwise as is going to be corresponding with positive torque about a fixed axis. Or they make the same connection with rotation. If something is rotating counterclockwise, they consider it to be positive. In your homework, they use this notation. This is counterclockwise, and it's considered positive, as viewed by you. Okay, so now if we have clockwise, this would be the case where, let's say this is the lever arm. Here is the rotation axis. Let's say the force is going, let's say, in this direction. In that case, if I press in this direction, it tries to rotate the object in this direction. And this is what's called clockwise, just the way a clock rotates around. And so clockwise is what your textbook calls negative. I will just call it clockwise and counterclockwise, though. Okay, I didn't draw the little angles here, but you can draw the little angles between the two, the force and the lever arm R. So the lever arm is this vector, or this position vector, going from the rotation axis to where the force is acting. These things here mark the rotation axes. Okay, the next thing I want to talk about is adding or subtracting torque. We can add or subtract torque. But you have to pay attention to clockwise, counterclockwise, or clockwise. Okay? So let me give an example. Suppose I have here, this is the rotation axis. Oops, sorry, I was off the screen for a moment there. I have a rotation axis here, and let's say I have one force is pulling in this direction, say 90 degrees, F1, and I have another force here, F2, pulling this direction. Okay, even though the forces are going in opposite directions, they both try to make this pen, this is rotation axis, so I'll pinch it here. If I press here, it tries to make the pen go counterclockwise. If I press here, it also tries to make the pen go counterclockwise. So in each case, both are counterclockwise. Okay, so they both are trying to make it spin around this way. So they add up together. If I have a situation where this is a rotation axis, this guy is F1, this guy is F2. Okay, these actually have opposite effects on the torques go in opposite directions. This tries to go counterclockwise, whereas this one tries to go clockwise. Okay, so one goes this way, one goes that way. Counterclockwise versus clockwise. So the torques go in opposite directions. Okay, so F1, this is going to go in the counterclockwise direction. Okay, whereas F2, that one is trying to make it go in the clockwise direction. Counterclockwise, clockwise. The next thing I want to mention is that if the force and the lever arm vector, this R vector, position vector, note that if F is parallel to R, then phi is equal to 0, and the torque equals 0. Okay, so let's take a look at this. Suppose we have this is rotation axis. Remember, this is just, we're looking at it dead on, so the rotation axis is just this line that's coming out at your eye. Okay, and this is my lever arm, and going from the rotation axis to where the force acts. But let's say the force acts in the same direction as R, that's what I've set here, parallel to R. Then the angle between these two, phi is equal to 0 degrees, and so tau is equal to R times F times the sine of 0 degrees, but the sine of 0 degrees is 0. So there's no torque, no torque. But this is something you might expect if you just pull on an object like this, you're not twisting it one way or the other. I should also mention, if F points opposite to the lever arm vector, then phi is equal to 180 degrees, and the torque is also 0. Okay, to see that, we have, here is the rotation axis, rotation axis, and if I have the force going directly like this, then the angle between the two will be 180 degrees. And then we have the torque, the magnitude of the torque is R times F times the sine of 180 degrees, but this is also equal to 0, so the torque is 0. So that makes some sense, I think. We have here's the rotation point here, and then we have a force, but I'm pressing in. That does not do any twisting one way or the other. So the torque is 0. Remember, to have a torque, you have to twist something. Now, we can also write the torque in a different way. We can also write that the torque, magnitude of the torque, is r perpendicular times F, where r perpendicular is r times the sine of phi. Okay, hopefully this is not too confusing. If I take r perpendicular to r sine of phi, then I would end up with the torque then is equal to r perpendicular times F, and so I end up with the same formula I had before. Okay. However, there is a different way of interpreting what's going on here. Geometrically, the notion of r perpendicular is the closest distance to the rotation axis for a line passing through the force F. Okay? I know that is a little hard to understand, but I'm going to draw a picture that clears it up. So, we have, here's R, here's our rotation axis. Okay, this is R, and let's say the force acts here, F. We have some angle phi. Okay, the line passing, when I say the line passing through the force F, I mean you draw a dotted line through the force. It just slices along, lines up with the force vector. Now you look at this line and ask what's the closest distance to the rotation axis. You get the closest distance, you start from the rotation axis, and you go perpendicular to the line here. Okay, that's why it's called r perpendicular, by the way. And then this distance, what is this distance going to equal? Well, this angle here is also equal to phi. These are what are called vertical angles. These are the same. This is the opposite side to phi. And so this one will have length r, plane of r, magnitude vector r. And so then this will be the opposite side, and so it's equal to r times the sine of phi. So this is what we call r perpendicular. Okay. So we can write the torque as r perpendicular times F. And in some cases, this will be an easy way to do the calculation. It's especially easy when the force is either horizontal or vertical. You may find that doing calculations this way is faster than using the other formula, r f sine of phi. Okay? Both expressions are fine. Okay, there's also another name for r perpendicular. R perpendicular is also is called the moment arm. Of F. But I just call it r perpendicular. Nothing fancy. Okay, we will come back to torque as a vector. We'll say more about this next time, but I should just mention it for now. Torque is a vector. However, for a fixed axis, fixed rotation axis, it is enough to say if it is counterclockwise or clockwise. We already said this, but I just want to emphasize it. We'll come back to the notion of torque as a vector. All right, I promised that we would now make a connection to moment of inertia. Otherwise, last lecture we defined moment of inertia and never really did anything with it. So now I'm going to make this connection. We're just going to do a whole bunch of analogies. Okay, so this is Newton's second law. We already did Newton's second law, but this is for the angular case, for angles. Or if you don't like the word angular case, for rotations. Okay, so let's define the net torque. This will be net torque. That's the sum of all torques on an object. Remember, you have to keep track of counterclockwise, clockwise. So your book likes to think of counterclockwise as positive, and your clockwise as negative. So you can use this symbol. Counterclockwise equals plus, clockwise is equal to minus. And that will keep track of the orientations. Now, then we said we have this moment of inertia. Okay. And we also have angular acceleration. Now let's try to go back and recall what these analogs are in the linear case. Okay, so for rotations, for angular motion, tau net, that's net torque. But if we had the linear analog, this would correspond with F net, the force, net force. What is the linear analog of moment of inertia? We said that's corresponding with mass, m. What is the analog of linear analog of angular acceleration? That's just plain old acceleration, a. So now what we can do is we can take what we've learned from the linear case, F net is equal to ma. Let's just work with the magnitudes of things here. And we do the analogies. We get tau net is equal to moment of inertia I times the angular acceleration. And just by doing that, we have Newton's second law for rotations. Okay, quite simple. Let's do an example of this. Let's say we have a uniform solid cylinder, has radius 2.0 centimeters and mass 1.5 kilograms. Let's say a tangential force. Tangent means that it's, remember this whole notion that tangent means it's touching the surface and just balancing on top of it. That's tangent. Okay, a tangential force of 5 Newton acts on it, the cylinder. what is the resulting angular acceleration? Okay, we have a tangential force of 5 newtons on this solid cylinder. Let's take a look. Okay, so we have this cylinder, and then we have some tangential force acting on it. So this is, I'm trying to draw a three-dimensional perspective of the cylinder, but if you look at it from the top down, what's going on is this force is tangent to the circle. Okay, if I view it from above. All right, for a solid cylinder, we know that the moment of inertia, I, is equal to 1/2 mr squared. This is what we did last time, last lecture. And so we have 1/2 times the mass, which is 1.5 kilograms, times the radius. We said it was 2 centimeters, so 0.02 meters squared. And that comes out to 3.0 times 10 to the minus 4th kilograms meters squared. Okay, remember, moment of inertia has this funny units of kilograms times meters squared. So this is our force F. Let's calculate the torque of F. It's going to act at a distance. So this is the center of the sphere, so that's the rotation axis. Okay, so the angle between the this moment vector here and the force will be this angle of 90 degrees. So these are both at 90 degrees. So we have tau is equal to r times f, okay, times the sine of 90 degrees. All right, I'd call this capital R, so might as well use that same symbol, capital R. All right, so what is capital R? Capital R is 0.020 meters, so 2 centimeters, times the force, which is 5 newtons, times sine of 90 degrees is 1, so we get 0.10 Newton meters. So this is the net torque, I should have said. There's only one force we're concerned with. And now let's use Newton's second law for rotations. For the angular case, we have tau net is equal to the moment of inertia times the angular acceleration. So we have this for the net torque. I, we found, was 3.0 times 10 to the minus 4 kilograms times meters squared times the angular acceleration. So the angular acceleration will be 0.01 divided by 3 times 10 to the minus 4. Is equal to 333 radians per second squared. Okay. By the way, if you were trying to keep track of my units here, I put in radians out of thin air because angular acceleration is units of radians per second squared. But you'll notice that the radians aren't really a unit. You put them in when you need them, and you take them out when they get annoying. Okay. All right. The next topic is about the kinetic energy of a rotating body. And the formula, K rotation, is 1/2 I omega squared. And we can get this directly from the analogies. Okay, so let's do the linear analogy. This is just plain kinetic energy. This is what we call translational kinetic energy. That means the kinetic energy associated with the movement of the center of mass, how it translates from one position to another. And then we have 1/2 mv squared. And so now we just do the analogies. Mass goes to moment of inertia. As velocity goes to angular velocity. Okay, so this is the formula for the rotational kinetic energy of the rotating body. Now, if an object is rotating and the center of mass is moving, then we have both. We have both the translational and rotational kinetic energy. I realize maybe I should have put here rotational kinetic energy to label this equation, rotational kinetic energy. Okay. So if I want to know the total kinetic energy, I can write this as this is total. This is the rotational, K rotational, plus K regular translational, trans, if you want. And so this will be 1/2 moment inertia angular velocity squared, where this one will be 1/2 m, and let's call it V's center of mass, the center of the rotating body, center of mass squared. And so the total kinetic energy is going to be 1/2 I omega squared plus 1/2 m V center of mass squared. Okay. Let's move on. Let's do an example. Let's find the kinetic energy of a solid. Let's get the kinetic energy of a solid cylinder of radius 40 centimeters and mass 1.0 kilograms, rotating about an axis touching its surface. Okay, so the question, let's say the angular speed is 3.0 radians per second. Okay, that's the omega. All right, so we have this situation. We have a cylinder, and it's rotating for some reason about an axis that's touching its surface, like this. It's a solid cylinder. So in order to get the moment of inertia about this funny axis, we first need to know moment of inertia about the center of mass axis here, and use the parallel axis theorem. Okay, so I about this funny axis will be I center of mass plus the mass of this object times this distance separation, which is r squared. So remember the formula, there's this extra mh squared, where h was the separation between the two parallel axes. In this case, the separation is capital R. So now the moment of inertia about the center of mass for a solid cylinder, so this is solid cylinder, is 1/2 mr squared plus mr squared, and that gives 3/2 mr squared. And we can plug in the values, and we get 3/2 times 1.0 times 0.40 squared, and that comes out to 0.24 kilogram meters squared. Now the last step is to calculate the rotational kinetic energy. That's 1/2 I omega squared. So we have i's here. We have 1/2 0.24 times omega, that's given up here. Omega is 3.0 radians per second. Square that. And so we end up with 1.08 joules. Right, if you have any questions, please ask the student supervising today's lecture.